my lecture will be on energy efficient and intelligent IoT devices. And before to start, of course, a little introduction also to cover the objective 2 that the organizer mentioned yesterday on making networking. I feel this topic is quite interesting to have a vertical vision. You will see that we are going from sensors, processing, energy efficient and energy harvesting, and also I will show a bit of application, but I think is, in my opinion, a good opportunity topic for discuss with your colleague, but also two words on me. I'm currently senior scientist at this project-based learning center that burn like a teaching center, and we are hosting a lot of PhD students, but mainly we are doing research on embedded system and smart sensors. This means that whatever you are going to see here, it's partially covered by my group, so I think if you have any idea, you can also discuss with me. And also, I'm currently have also some position in Milan, in Italy, in Sweden, and probably will have another in France, so it depends where you are. We might find a way to cooperate also with other groups. And also, feel free to interrupt me. I know that you have a different background, so I try to have a general overview, going a bit deep in details. And also, as I mentioned, we will see 4 different topics in these 4 days, but of course, we have a general overview on an IoT device and why this energy efficient intelligence is so important. And actually, you see probably that in the floor, there's a little drone here. You will see that mechanical is an issue. Electronics work very well. No, I'm joking, but you will see a little demo. I hope it's working, but I have a real mechanical issue. But we will see a drone, but especially we start with the main topic, that IoT devices, and what you saw that is a recent trend. And probably you saw already in the presentation of the keynote speaker yesterday that actually opened very well my my lecture, because many things he mentioned you will see also in my introduction and during all the course. But one recent trend that you know very well, in this case I selected one, let's say, vision of material IoT device that is wearable for the simple reason that, or watches, is that this is a very clear to understand what is it, and the majority of you have here. And if you just think about a few years ago, later, what is happening from your smartwatch to your smartwatch today, you are wearing it, is that you have incredible and significant increase of hardware and software capabilities. We started with an analog watch. We just see a quartz telling you what time is it. Now you are reading your mails. It's telling you when you are going to burn 3 kilometers, 300 calories. You are doing many more things that you were expecting only a few years ago from your wearable. So it means that inside hardware and software increase significantly. So we have much more sensors, we have much more processing capabilities, and in general, we also are seeing that there is more intelligence. Of course, I promised myself don't say ChatGPT, but I say only once in this talk. Everyone is thinking artificial intelligence is ChatGPT, because it's telling you how to write a paper, introduction of the paper, etc., etc. In reality, many things are happening in edge computing and low-power devices. Because when you are going to run, before, I don't know if you notice, but before your Fitbit, it was sending information to your phone, it was sending information to the cloud was telling you that you were running. Now, there is a little neural network inside to your smart bracelet that without internet connection is telling you that you're running. How? With a little model that is neural network, artificial intelligence, you can call how you want, but it's a little model that, according to the sensors data, is transforming this raw data in an information. How? Adding new sensor, because more IoT devices are using a combination of sensors. This will be my demo, actually, to make the same job in more energy efficient way. Why I'm stressing energy efficiency? Of course, this is a topic of this class, but also because you know very well, this is the reason why I select one of millions different IoT devices in the world that is battery operated. And you know very well that all these nice functions are very nice, and you might want even more functions. But you are limited by the battery lifetime. And again, this is one aspect. So we know very well that the trend is also that our smartwatch now is a little bit changing, but in general, the trend is that the watch that you were using, the Swatch of 15 years ago, was lasting 6 months. Your current watch doing all this functionality is lasting 1 day, best case. Okay, 2 days if you really don't use it. So in general, the trend is that we are assisting, of course, having much more intelligence, but actually the lifetime and the size of your watch, you believe that this is only for display. It's also for the display. But one reason is that you have more space to store your battery. This is what we are going to see in lecture 3, that unfortunately, the battery technology is not scaling. If you take the exponential growth of your hardware and software that we are assisting, also the sensor, in the last 5 years, the battery has the same capacity. What you have inside on this battery today with the same volume is probably 5% bigger versus the technology that meantime is scaling very up. So this will be the reason why we are continuing to push in energy efficiency, because people still want, and hardware still is capable to do more, but has to face the limit of the battery, and this also is the reason why actually it's nice to do research on making intelligent with this constraint. Without this constraint, the job was too easy. Take ChatGPT, put in your watch, job done. So why you need to struggle with a little node, new sensor, other things? You have, in theory, everything. And the second time says ChatGPT, so now my bonus is done. Because we will not see this bigger model. And what I'm going to see is actually the potentiality of sensor processing in particular. Actually, I was very happy, but not surprised, to see that many, so I'm expecting many of you, are doing at least one course with the RISC-V processor. And this is for mainly the energy efficiency, but also to extend the potentiality, intelligence. So we are going to see also, so I tried to put the connection with what we are going in this more vertical lecture, where we are going to see different topics, with also what we are going to see in other courses. And this is just a strange, different topic, because I believe this can be very interesting, because today we are assisting to have hardware and software that actually are starting to match the energy that you can get, for example, for a little solar panel. So it's possible or not, depends on application. For example, before someone is asking, we will never see a drone flying with a battery for next at least 20 years. Because the energy we are getting is much lower than what we need for the motors. But what we are going to see is a push on, for sure, energy efficiency and also smart sensing. And this will be my introduction topic, and show what are the key challenge and a little bit of theory, but more challenge, trend, and examples, starting from today, that this is a topic that needs to take in account the full view of systems. It's not only processor, it's not only the sensor, it's not only the energy of the battery, but it's a full view of the system. And we are going to see from the concept of cyber physical system, this I will introduce few words in a few slides, to the evolution, because I consider IoT a kind of evolution. Cyber physical system probably, if you see some papers also from 10, 15 years, was already someone talking about it. IoT is a kind of evolution, because at the end it's doing the same job. Take information from the sensors, processing, make an action. This is the reason why we call cyber physical system. And then we are going today to see the importance of energy efficiency, the trend of the people that are designing new hardware, new sensors, new application, new systems to target this energy efficiency, and then identify the component that can be useful. In particular, we have only 5 days. I target this set of the 5 classes in processing, energy harvesting, more intelligence, because I'm pretty sure you would like to see this machine learning, tiny machine learning running with sensor processing in an energy efficient way, and then a full system overview. So this is more or less what you're going to see. And I think, can we do this in 5 weeks? I think so. So I think probably this is more from you than from me. So you need a feel to be awake at least 50%, not of listening what we are saying, be in the class, but I think this will be probably the case, and of course not think too much of the lunch, because actually the main interesting things probably I'm saying at the end of the class. Seems strange, but I need to introduce kind of a different topic in all the lectures, so I think the conclusion, I feel, are the key of the class, so it's very important to don't think that you need to go in 5 minutes there. So this is the organization. I think you have the slide, you already saw it, probably you are ready to do it. So before to start, do you have any questions? Then we start slowly with a few demos. So you still like it? Yeah? Yeah, sorry.
Yeah. So I was just going to tell you, you will mostly focus on the ways that we can apply to a single device to save energy, right? Not to a network of devices.
Yes. So this class is more focused on a single node. So I'm not looking for a networking, because this will be over the 5 weeks that we have today.
Okay.
But the idea is increasing the intelligence and energy efficiency of a single device. This, of course, can be applied to a multitude of devices, but I'm not going to see the efficiency of the interconnection of different devices. So not a network of devices.
Okay.
Yeah.
Thanks.
No problem. Okay. Any other question? Curiosity? I'm starting with some little introduction on cyber physical system and drones. Yeah. Yeah. Sorry. Yeah, I think there are people online, or they are recording for the online version. We need a microphone.
Yeah, just out of curiosity, are we going to see any overlap between this topic and approximate computing? Because usually in our papers, approximate computing, we always refer to IoT devices as being super error tolerant, and there are more room for exploiting energy efficiency while you apply approximate computing. Or
yes, I believe, to be honest, I didn't check all the slides from the other courses. So you might answer to the question later better than me. So from the abstract, I tried to be in the way that is a constructive overlap. So I believe that the reason why I'm doing tiny machine learning, the way that I'm going to see the quantization, the reason let's say I'm really going a bit lower level on the hardware. And this is also the reason why there's a few topics that are a constructive overlap, in my opinion. Then I think you are the one doing evaluation, actually giving us feedback will be important. So I think I did it, let's say, reading the abstract, but it's, this is you can tell me later better, but I'm pretty sure you will find some things interesting and covering. Also for the RISC-V, I introduce it to leave you the opportunity to go to see. So I'm not going deeply in the RISC-V, but I'm saying why, for example, RISC-V could be very interesting for the tiny machine learning or the smart sensor. And actually, I'm showing an example already today where this is true. But of course, today is just to attract you more, to be more motivated. So you will see this in the course of the 3 weeks. Okay, so more or less, I think from the class you have everything. Any last question? Then I start, but we have a bit break again with the demo. So in general, as I mentioned, I see this an extension of an embedded system. So I'm bringing these 5 weeks like an embedded system lectures. So you will not see the architecture or how we design a node, not the processor, but really at the system level. And this for putting everyone in the same page. I know you are different background, you are following different courses. I think in general, this was traditionally called to information processing system embedded in a larger product. And also we can see that actually with IoT we have a full product that is an embedded system. But this could be go from robotics, could be to big machine, cars, Internet of Things, of course, is one of use of embedded system. And actually, what I'm trying also to put in these lectures is the way to somehow exploiting this energy efficiency also to other application scenarios. So actually, I'm pretty sure that, but this again, in 5 years you can come back to me, that at least a good 50 to 70% of people are going to see something similar. In the same way, having a challenging, constraint, you put your large models that I don't want to name anymore in some things that has hardware constraint. This is because I said yesterday I liked particularly the keynote speaker, because it was really highlighting this important aspect, that anyway, there is constraint, there is the edge, there is the clouding, these I'm taking back from here. And the efficiency, don't think only to the battery. As I mentioned before, I put this to attract you, also the drone is one of many similar devices that has the same constraint, are working with sensor, they need to do signal processing, or in general processing information in an embedded way to get observing and influencing. This is really the key of embedded system and cyber physical system. The only reason, there is many people writing many things different, especially if you read papers, you see many people write the cyber physical system some things different. What is it is, for sure, has to be something similar. There is the physical world, we are observing the physical world with computer, system, embedded system is a little computer. We are trying to make an influencing the world. IoT seems not doing, if I watch, is doing, because they are sending information to you to get some extra information on how you are running. But in general, sometimes this can be only the communication, sometimes can be really your embedded system controlling your car. So today, probably you know, Tesla, Google, Amazon are employ people like you in doing chips, processing, sensors, and making embedded system out of it. And they are car companies, or they were delivering books companies. But they are working in drones, they are working everything is a cyber physical system. So again, I don't know where you are working in all these big pictures. You can work on sensors, processing, compiler, software, models, whatever, but we'll more and more going in direction of having some cyber physical system or IoT there, because there are plenty of them planned to be there. And as I mentioned, one other example now that we're going to see is really the little drone. I like little drone for a simple reason. This, whatever you are going to see can be applied also to bigger. Why I selected the little? Why actually we are doing research using it. We are not doing research in a little drone. Actually, we are using it to have constraint a challenging even more strong. Because if you have the energy and the latency together, even harder. Because you don't have a huge cloud to make it work. And in general, why do people like Tesla, they are going to have this vision? Because these two transmitted information make all reality. It can be one branch of it. But at the end of the day, you have your Tesla that is stopping your car in 100 milliseconds. Best case. Even if you do it faster, it's even better. And this will never be possible even with the 5G, 6G, 7G, 9G, 25G. Because until you are transmitting this information, you are killing some person. So when we are talking about energy and the systems and cyber physical world to influence the world, this will be for next 100 years. Especially because more and more we are pushing in automation. We are pushing robots. These robots need to be how we are. You are looking this unknown ChatGPT to your paper last time. But what are you without the connection? How slow you are with taking this information versus you write directly a book to do your exams. Right? You need to write without any connection, or if you don't have this connection. So in general, what we are doing is distributing the energy to the edge with something similar. Your eyes, your sense, your intelligence, and action fast. Even maybe worse, but fast. And this is just an example, so what is happening. This is not our, so this is work from another group in ETH. In general, and actually they are using external sensor to influence the world. It's an embedded system, seeing it, in reality is coordinating with some external help. And also, but you can saw the potentiality. This is a controller, is flying, is setting the swarm, and is going down. And then there is even many more attractive, actually I'm very impressed from what they are doing, attractive talk that are using the same drones. This I want to show, this is not only a toy. but it's also some things that people are doing for sure. Here, actually, I don't have enough information to tell you 100% what they did, but I believe they use the light at the external camera to do it. And what I want to show today is that this drone never saw this house. Actually, you will see that I have a mechanical problem, but this drone never saw anything here, is off, is never trained for this room. I don't know if you see me, I was busy with my daughters around. I didn't have time to come here to set up this drone here. This I tried, of course, in the lab. There is a lot of people working on it that I thanks a lot. They are all the people from my group. They are PhD spending years on it, on the sensor, on the processing, what we are going to see. But these things arrive here without knowing nothing, even with some damages. And I hope it's working at least for 20 seconds. Because these are very, very interesting. But in general, I did also this demo in another, this is still not ours, but these are doing so this is a video, of course. The idea is that really bringing these little drones in mission that the bigger one are not able to do it. Passing the little space, going in some, looking for person in a room and a firefighter. So this can do in future job, I believe so. They need to have fully autonomous systems, fully, working with the high constraint. The battery, it's the highest constraint. This node lasts 5 minutes, this battery. So this actually, I hope is the meantime I didn't discharge the battery. But in general, it's only 5 minutes. But the motor are the more complex one. And before to see actually what we are going to do, so I think this is quite interesting. Again, I put it also to be a hot topic. I saw a lot of very nice topics. So I hope I convince you that embedded system, energy efficiency, intelligence could be some things very interesting for the future. There are many aspects to keep in mind, and especially because these are, as the watch, complex system. There is the motors, there is a couple of microprocessors. This, of course, is a specific case. So we didn't design the hardware. We are buying, this is the Crazy File 2.0. We are buying the company, but of course we need to extend it. There is a little microcontroller inside. 168 megahertz, ARC Cortex M4 microcontroller, very old, but it can do some processing. There is very little memory, 1 megabyte. The other part is fully dedicated, is the Cortex M0, fully dedicated to the Bluetooth connection. There is, of course, 4 motors, some expansion board, that actually this was one of the reasons why we decided to use this processor, is because we can expand this little drone with our own sensors to increase further the energy efficiency. There is, of course, the motor driver. There is some sensors on it. So it's a perfect embedded system. It's a cyber-physical system, yes. It's reading information from the sensors, is adapting with SPWM the motors, and at the end you can even expand with future sensor. Why? I will tell you in a while. So there is many components. I think the details, you have the slide, you can go in. It's nothing special. 2 microcontrollers, sensors, PWM to control the motors. And why I'm bringing this not so special processor to here, because as you saw, many interesting talks are going there, and also because we extended it to the 3 of the 4 things that, sorry, okay, for some reason I lost the, I tell you, so it was a list, probably in the slide you have, there is a list of the extra component, but we will see also in the class number 2 or 4, if I don't remember wrong. In general, what you will see in this demo is that we attached 4 different little time-of-flight sensors that are giving you a matrix of 8 by 8 little pixel with already pre-processor information. So you already have the distance from this different object. Why this help? Why this is going in energy efficiency? Again, we will see a bit better tomorrow, but in the demo, what you need to think is that you actually remove the needs for the processing this information with the 2 cameras to have a stereo vision. You have already a depth camera having the depth information. So you can exploit this information to run some machine learning, signal processing. And we put 4 of them. In reality, in this deck, we also added a GAP9 processor that is an 8-core RISC-V with an hardware accelerator we are going to see next time, to see that you can even extend the processing capabilities. Why? What we are going to do is extending hardware and software capabilities. Why? Because this drone, without seeing this environment, I think is working. I will show you that is able to land in 7 seconds. So I will switch on it. It will land, it will, take off in 7 seconds. I have 40 minutes to make him a bit crazy, and this will be the risk to lose a propeller. So when you see that this flip is, because one propeller is a little bit broken, it will fly away. So when you see flipping, you believe it's electronics, you will see that a few seconds later a propeller coming down, but I hope it's not happening. So in my room sometimes it was working also with this broken propeller. I order others, so I hope it will arrive here Friday. At least you will see the full demo. But in reality, what this is planned to do is take off in 7 seconds, have 40 minutes of free flight, try to go back to the original position, but as all 40 minutes, wherever it will be, it will land. But it will find a landing spot to land alone. So this is how it's supposed to do. And of course, again, there is this mechanic I hope we will see, but I will show anyway the demo in case, the video demo in our lab. And actually, we reduce the speed for your safety. So actually, in the demo, it's going much faster. So in this video, I'm doing later. And in general, this I'm using also at home. So this is the reason why I have 3 daughters at home of 7 to 5, because they are trying to catch it. So it's ultra safe. This is also the reason why it broke, because sometimes it's failing to make an avoidance, so it's crashing somewhere. So it's not always perfect. But you will see that, I hope, again, it's lasting at least 20 seconds in what I want to show. So it's already not flying away. So in general, it's really going away from me. Now it's going there, he noticed there is someone, but you can really go to try to put him. So now he sees something's there, and he's trying to go back to my place. Of course, until I'm there, he will never come. But if I go away, he's even resisting more than I was expecting. In general, he's now re-looking where I'm helping a bit him to go. And maybe I will leave him, so now he's, of course, a bit lost in where to go. But if in 40 seconds, I think he's resisting a lot. Now I feel he will look for, I leave him alone because I don't want to stress the motor. So I'm leaving more for don't make the fly the motors. He will, now he found a place to land, he's landed. And again, I a bit help him, but in general, thank you. So not always work. Actually, I won't try again because if I stress too much for the motors, now I want to tell that actually always mechanical is a problem, but it didn't work. But so I think meantime I go on, I think now I can make it more hard for him. But in general, again, this is a completely autonomous system. Of course, it's doing some things basic, but this is, again, not even very trivial. Because when he was going there, he noticed that there is some things there, and they're stopping it. It's a camera-free system. So this doesn't need any camera, for many reasons. Also because if you put a camera, so you will see that it can do another trajectory. So it's really not programmed. Now you will see some things will fly down. So it worked that mechanical is a problem. So I don't know, but at least the first demo is working. So I knew that this was going to happen. So the reason is that there is a little break, crack that I cannot see where is. So I tried to glue wherever, but still is happening. So I think it's actually the reason why it worked. Probably this glue helped this minimal to last 40 seconds. But if you do something strange, it's giving pressure to crack, and this is flying away. But it's ordered, so you will see that you can. And again, this usually is the game of my daughters. So I think they try to catch it, and it's quite safe. But anyway, I did the demo, so I think we can anyway spend a few seconds to see demo. So I think this is a very introduction. I want to anyway then give some technical tests. But in general, these are our test areas, and maybe this I don't know if you saw in time. So you can see this much faster in what we can do. Actually, also here is not the full speed that we are putting it. So of course here I'm slowing down because if I run, it's going in the face of someone. It's better giving time to understand what that is going somewhere else. and going a bit slower. But in reality, it's going very fast. So look, it's going, so it's avoiding walking, running people without any problem. It's also very interesting. This seems trivial, but it's not so trivial, because you need to work with the control and the sensor to stay in this little tunnel. So if you take it also, controlling is hard. So if you control with your remote control, easily you will crash it. So in general, these are extra functions that are actually, in this case, we are using even only the time-of-flight camera. In reality, we are working even with a little event-based camera using this. I was thinking don't put, but I feel at the end I will put it, using a neuromorphic accelerator inside the same GAP9 architecture or similar architecture, the Pulper is 5-core, to even adding an event-based camera that consumes only 40 milliwatt of watt. I don't know if you know what is event-based camera. We discuss. I have to see where I found the space between tomorrow and the fourth on the 5th class, maybe an example, because this is very interesting. And again, we are using it to go to the extreme. I'm pretty sure if you see some demo with event-based camera, if you are, or if you know what is an event-based camera, but it's a camera with giving spiking, everyone is using, or almost one I know, they are using images from USB stick, USB camera that consume 2 watts. And they are touching often the GPU to do it. And you will see that stressing in the energy efficiency, we were able to do in 50 milliwatts with actually the combination of the hardware design that come from the group of Professor Benini, that we work very close together, that we have a device interface directly inside to a RISC-V core. RISC-V base processor is not a core, it's a really system chip. And what we are using for the demo, the same. So at least to target our power budget. But on this, I want to actually finish on talking of the drones, because the drones I'm putting really to get you motivated to follow it and show that actually this benefit in energy are also resulting in latency. So I started my, let's say, PhD in, at the time we didn't call IoT, but were wireless sensor network pushing on energy efficient to survive in batteries. So we wanted to reduce the power consumption to save the energy to last more. And how we end up now to have robots? Actually, we are also, in my group, we are also using sensors and embedded system to win competition to autonomous cars. How this can be so different? And I feel it's the same. Because what we were stressing in reducing the power is actually help to reduce the latency. Because when you are going to understand the hardware what it can do to remove an extraction, to do 2 cycles more, you are basically, if you have a battery that you need to live more, 1 instruction and 1 clock less is years of life. There is 1 millisecond is a winning competition or don't kill a person. So actually are 100% the same in my opinion. Yeah.
So the thing is, as you mentioned, I think you mentioned earlier that, for example, for the drones, a lot of the power is going for the propellers itself. I don't know what is the exact number for the energy consumed for the computing and all, but I think it can be even negligible.
Yes, this is a good question. It's actually the things that we are always reply to papers for reviewers. So in general, this is 100% correct. So at the moment we are using 1 or 2 watts for the propeller, and we are struggling saving 100 milliwatts for the drone. Actually, in this case, I'm not showing, but why we like this time of flight is for their weight, because actually adding weight is even in this case more constrained than adding a processor flat that is consuming nothing. Okay. But in general, you cannot even if you go higher, you need to remember yesterday, you need dissipator, you need a much bigger, so in general, the step to go higher, it's possible, yes. Bigger goals are possible, yes. But in this case, we are going to see like a research aspect to see to what a little processor can do to really have boundary.
So, I mean, again, I don't get the goal here. The goal is to maximize the performance then? Are you,
So the application goal here is increase the autonomy in some things that you cannot put anything more on it.
so essentially, it will be performance. Then.
Yeah, if you put a Raspberry Pi here, you are already dead. Because you are going in comparison of these 5 minutes become 1 minute.
Okay.
So today you cannot have anyway so much margin. Then if you tell me, of course, the 20% it's the processor, but 100 or 80 is the propeller, this is true. But here you are really anyway boundary it. But in general, we are more seeing the research aspect. Then if you use in this drone, if you use in your watch, if you use wherever, it's the way to treat the information with most the energy efficiency way. So this is what we are going to see. This is for me, it's an example. And for us, it's giving challenges. Because this is making us looking for different sensors to reduce the efficiency, so increase the efficiency, see the different way to do machine learning on it, looking for a processor that can give with the same amount of power the more capabilities, like the RISC-V multi-core. So we set the boundary. We won't stay below 100 milliwatt of power. You can go under 50 because you have, yes, you can. But in general, this is our target to give the aspect. And this, in other applications, you can have the same constraint. Remember, this for me, it's an example. We are not doing applications.
So if I got it correctly, they're using energy efficiency is kind of a constraint, not the goal here. Then, if
Energy efficiency is our goal. So we want to push on technology to do the same job with the minimal energy consumed, with the minimal time. This is our research goal.
Okay.
And sometimes these are linked, because you can tell me I take a GPU. No, because if your limit on, if you go higher power, you can always go higher power.
Yeah, but that's a different class of processors.
Yeah, but
I mean, for example, if you go embedded to server, for example, GPUs, of course, that will be very different.
this is actual exploration in new processor. But the boundary is always 100 milliwatt of power. You have this boundary in power, and you need to do the best in energy efficient with the sensors, with the processor, working on the tiny machine learning. We see this aspect, how this effect in power, this I'm introducing already today, are bringing a limit on the processor. So the power actually is limiting everything, because there is no magic in electronics, as you mentioned.
Okay, yeah, so that's the thing.
Yeah.
So, but don't you think choosing the right, or the, let's say, the right kind of, I mean, okay, I'm coming from the kind of the process domain, but I'm just thinking that choosing the right kind of combination of accelerators for the drone will be more beneficial than, for example,
You can so actually we change the processing power. So you will see in I think class 2 or class 4 that already in this introduction that actually we show the benefit of having the same limit of below 100 milliwatt in moving from an ARM Cortex M4 to 8-core RISC-V with hardware accelerator. This is the trend. The trend I'm showing for processing. To reply to your question will be next week, tomorrow, next class.
Okay.
But again, there is no magic. You need to put the boundary somewhere. The boundary today is the power. Automatically, with the power, you are there. Then you can. I will show the trend that with this boundary of power, that is to everybody, this boundary of power are actually stimulating people like you or the people who are doing processor to stress on new technology, new transistor, new instruction set, new compiler, unitary machine learning to, with the same amount of power, doing a better job. This is a trend from the beginning. So the battery is really to fix this. For us, the boundary is the power. And the idea is then the same component as also helping to have energy. But, for example, for the car, if there is no reason to use a microcontroller. If today you can use a GPU and the power is getting there. This has to be clear. So if you change your boundary in power, are changing the hardware you are using. The methodology doesn't change, because at one point you have a boundary on the hardware. Because the car producer say, more than this power for your edge computing, you cannot use. At this point, it's arriving, for sure. It's power or cost. But at one point, they fix you. Power is fixed, and what you can do is there. Methodology doesn't change. You need to look for a different processor. You need to look how exploit the hardware down. So I think this is because I like the keynote. If you are very high level, what is up and down, it's impossible to know. And today, this, in my opinion, and what I want to pass to you is the key. Actually, today you need to look the hardware because it's moving very, very fast. And you need to look at the software because it's moving very fast. Are two hot areas going in parallel? And what is inefficient today? More than if you see this other efficient. It is connection. Because if you have the transformer working very well, but no processor accelerating it, and you have a constraint on latency, what are you going to use? You have to do a trade-off.
Okay.
But if you, this is one of the key from the lecture 2 and 4.
Just a follow-up question.
Yeah.
So how much of this is actually specific to IoT? Like if you say you have like compilation as one research topic, what would be a compilation strategy that would help you IoT specific, or is it just generally like compiling faster? So
I'm an embedded system person. For me, everything is very important. So I'm actually the person say that you should go from the sensors to the processor, to the compiler, to the model, to the system application, and the application. And everything is important. And more on this pushing is important. IoT, I think, is one topic I put like a reference. Actually, I'm trying to show also other things. Because not only IoT. This is valid for everything. This is because I'm pretty sure that some of this aspect, the majority of you, we are going to see in your work in the future.
All right, so the idea is energy saving with the application being IoT. With,
Yes,
I guess,
in this case, it's more IoT because IoT is quite large to allow me to go a bit everywhere. But I really believe this is going to even things that are not IoT. Because a car, autonomous car, is not practically IoT. But still you are using the same technology from the software, from application specific, for the hardware that you are using. And for the sensor and the controlling part or the influencing the physical world.
fair, but I guess a car is a pretty large battery.
It's
so
too large, of course. I need to focus. In 5 days, I need to focus on something. So
right.
this is totally correct. So you cannot see everything forever. And what I'm focused in how exploiting sensor processing and tiny machine learning in a selected application. Because one thing that I always saying that I didn't say this time is that actually embedded systems is not existing general purpose. So an embedded system is an application-specific system, application-specific. The reason why I'm saying this, for me, it's, I'm not expert on application. I'm an expert on application? No, at all. I don't know nothing about application. If an application person comes to me, he's telling me, I need to run 100 millisecond fast reaction, 1 kilometer per hour, I have this boundary of power, this boundary of energy, and I do the embedded system work. Application is another field. But I need to work with people from application. Otherwise, I don't know any single embedded system well-designed that is general purpose. Because per definition, embedded system is doing a single application, covered very well.
Right, thanks.
Yeah, so these, when you see, are for me a sample to see where actually this research topic and methodology can be applied to real problems. Also, this was really, and actually we are sometimes taking count our real problem. But if you ask me where you are using it, I don't know. My real problem here is minimizing or maximizing the autonomy using different sensor and different processor to see how we can push in energy efficiency. Okay, so, and also, as actually your colleagues say very well, it's a huge work and there are many similar meaning for it. So this is also the reason why sometimes in the paper you are confusing. And if we go a little bit more specific, what is IoT? At the end, IoT is a physical object that is connected to internet. Also, this is the reason why it's anyway ultra wide already. Because internet means everything. Someone can think for his expertise that something's implantable in your brain because it's connected to internet. But in reality, an IoT is a multitude of object intelligent or with sensor, with signal processing that are connected to internet. So it's already say IoT, I'm covering thousands of applications. But what will be the main building block of IoT are here and you cannot change it. This is actually the reason why we are going to see it. It's from the computing, the sensor, the communication, the mains. Then, of course, in general, there is a natural interface because we are giving information to the user. So in general, we can see the IoT devices You can see that we are also in the cloud, but the things IoT, when we are talking about edge, we are saying at the edge IoT because we are referring usually to sensors. And why these are so diverse? Because also a car connected to internet is an IoT device. Because the things connect to internet. If it's collecting information, it's sending, this is an IoT device. Same for your watch, for a smartwatch, for a little temperature sensors. But in general, we have this trilateration between the devices that are the one at the edge collecting information from sensors. This is also the reason why smart sensors are so important, and I'm focusing the sensor and the processing of the sensors, and they can be connected to internet. In general, they are interactive with the persons. And more and more, one interesting, but this is for many years also, as I mentioned, a wireless sensor network is already 20 years, 25 years that I'm working. Probably people before me, they were working already 30, 35 years. But in general, more and more, we are referring more to smart sensors. And what is the main difference between a normal sensor and a smart sensor? What is happening today on going toward the smart sensors, and we see even better tomorrow, is actually the most important function that also when I was working, we were very little there, is the logical function. Why attached to the class 4 and class 2, the processing and the tiny machine learning? Because more and more we are moving to make them really smart. Maybe you can say that I'm cheating, there is some communication. These things, the communication we will remove to make lighter. So there is no communication on it. And in general, it's a fully smart sensor. Again, this you can use whatever you want because the processing is attached to the sensor, very close to the sensor. And this in general brings a lot of challenge because it's energy challenge, but this we are going to see. But also bring some, let's say, interest also from company today are pushing on this machine learning close to the sensor because you don't need communication, it's cutting the cost. And there is this wave of edge computing that I'm pretty sure many of you, even working in other areas, are probably working on it. If you're working in doing a new chip, a new processor, a new switch, what you are going to do? Likely, adding computational resources with the limit that we're going to see in a while. In general, this edge computing is bringing the computational resource close to the sensors or in general at the edge. Also your phone is at edge computing. And in general, why we are more and more talking about it is because I think I probably don't need to spend much more on it, but in general, we are assisting to have more computational resources, more application that they need to process the information. Your Fitbit is a very good example. So now Apple put also the ECG to make a vital sign monitoring on it. And more the trend is removing the information flowing from your smartwatch to the cloud to make the signal processing very close to your sensors. And of course, we need to have still various communication, so there is many challenging to face. And again, power is critical. And also, today I'm going to show is not only critical for battery-operated devices. It's critical for the cost, it's critical for the design of the processing, it's critical for everything is a power issue. And again, why I like the keynote, because he explained very well. We moved from the 86 processor from Intel was even needed to any dissipation to the needs of a supplier on it. So now we need to put a fan. Then of course, if you don't have any power critical, you might, the things are changing a bit. But again, improving the energy efficiency is always something to squeeze the processing to its best, making the hardware and the software connection directly. But again, we are going to talk in 1 second to the power because this is the main topic that I want to give you before to go to the lunch. And in general, you can see that this is a very old slide, and this there is always an update every 1 or 2 years of this slide with the innovation technology to the dilution of the technologies. No, this probably you saw many different in many different ways, but there is still a lot of interest on the Internet of Things, wearable, edge computing, i.e. to the edge. Because this still bring together the challenging of this architecture that we are going to see here. So however you call a cyber physical system device, IoT devices, wireless sensor network, a smart car, you are going to see things that include the sensor, the processor, the microcontroller, and the wireless communication. And also, again, this is very generic in terms of applications. So it doesn't matter what we are going to see for the things and which kind of microcontroller, microprocessor. These, again, remember, this can be changed. There is microcontroller secured. This can be a Raspberry Pi, a mobile GPU, can be everything in terms of what are your application specifications. So how you build these building blocks of the things is strong linked with your application. And I don't know 100% what will be inside to these things until I don't know the application and your specification. So this link between the application and the things is the one that make the design decision at the system level. When you're going to system level, you need to see what are your technology. Remember, we are not going, or at least in this talk, I'm not going to push in one specific technology, but how we can put these things or the architecture together to cover at the best the application that you have in mind and you are going to face. And again, I'm not going to see how build the microcontroller, but I'm going to show already tomorrow the trend of the microcontroller in bringing more hardware and more energy efficient blocks for your application. Any questions? Yeah.
Okay, when you're talking about smart sensors, how do you ensure the longevity of the algorithm that runs on the sensor? Because I'm pretty sure that it's quite easy to update an algorithm that's running on the main CPU or main, processing unit.
Yeah, in
But on the
general,
sensor,
again, here there is many definition to smart sensors. But in general, when we move from a real smart sensors that is autonomous and is working, this, I don't know which kind of sensor we're going to use, and which processor I'm going to use. But in general, the processing is done close to the sensor. So the new trend is today actually making processing cores inside the sensor itself to really go in the direction of making the real smart sensor. What is the difference of a normal sensor? Normal sensor is finishing when it's streaming out the data. So this is the difference. Of course, then someone is processing. But it's not anymore the sensor that is smart, but it's the cloud service exploiting your sensors. So this is the difference of a smart sensor. Then you can say I have a smart sensor application. It's okay, because you are giving a meaning of your data. And this is because I think this architecture, in general, is valid for IoT, smart sensors, and in general, edge computing, where we are really close to the sensor to process our information. Specification come from here. Do you have a boundary of latency? No. Probably the cloud is the best. So this is because I don't think that I'm selling one or the other approach. I'm saying that until you don't have the application specification, you don't have the real extracting the best from the hardware and software. So what I'm trying to show is how you can extract the best from hardware and software, having the full system picture in mind. This full picture, I don't know what is the best today, until I don't know the application. But if you target some things in the range of 50 milliwatts or 100 milliwatts, why I'm putting this boundary? This is the boundary for the most popular IoT that are battery operated. So again, I need to fix some boundary for you. Otherwise, we can talk of millions of applications. So if we fix this boundary, also this is the reason why I fix this boundary to have some reference in which processor is most popular to be used. Application, we are application specific. But today, the most popular processor to be used in this boundary are microcontrollers are the best in the world? No, there are many. I don't know what is the best. The best, if you ask me what is the best, if someone wants to ask what is the best, depends on application. Your boundary is the correct one. Here, there is some things better than microcontroller to do the job. In this application scenario where you need to run with 2 watts of power with motors and a battery of 350 milliampere hour to make it last intelligent, there is something better? An ASIC, yes, can be that this is the best. And I don't know the reason until I don't know 100%, I don't know the answer. So this can be, yes, can be a DSP, yes, can be a microcontroller, yes, can be an FPGA, yes, can be a microprocessor, yes, until I don't know the application specification, I don't know if you do the best choice. Because maybe you need to fly 1 second, be very accurate to shot this copy cap. This is because we need application specific. But the technology you are building in stressing and from a microcontroller 8 cores is 5 doing hardware and software, this will stay forever. So this is that you are extracting the best for your selection hardware and software. This is what I'm trying to show in this 5 class. And this approach doesn't change. Because if you go in DSP, you have limits. DSP is very good to do 1, 2, 3, 4, 5, 6 things. This is doing 1, 2. So you need to do the trade-off of your software that's up with the hardware you selected. So this is what I will try in these 5 days to give you in your mind that you will never reply, yes, this is the best I do, because I will never say this is the best, because we don't have application for it. But I'm saying, yes, with the specification we set to be autonomous, come here to do a demo, we didn't do for you. But we did for exploiting, actually the real reason to this demo, it's exploiting to the best this 8 by 8 time of flight to do mapping, planning, autonomous in a microcontroller that consumes 50 milliwatt of power. This was our goal. And today I can say, with the effort we are putting, this is the best you can do. The rest, if it is an architecture done well, I don't know. For our specification was the best we could do. For other application, can be another. This is also the reason why there are so many. It's also your challenge. So why the people are producing so many microcontrollers, so many DSP, so many DSP, ASIC, so many FPGA, for covering the huge amount of application and specification. Then if we put also the cost, this is even another boundary. And if you are a system person, you need to take this in account. Yeah.
I was wondering that what is the most fundamental operation that your processor does? I mean, why I ask is
the microprocessor, which processor?
Any operation. I mean, once you get the data, like you change it, you have the sensor, it senses the data and then it changes it into digital, right? So I was wondering that what is the most fundamental operation that it does?
So you mean really the basic are the ALU. So there is an ALU there that is doing all the calculation.
Okay. I mean.
But then there is many aspects to make this ALU work in an efficient way. So how they make the processor is completely different. This is the reason why you might go in one architecture to another architecture to an architecture that has a hardware accelerator, a mixed hybrid FPGA. So the world is enormous. This is actually the difficult of people doing compilator. That they need to know what is an hardware that is changing millions, to have a generic function the people doing in Python, and they need to match to do the best. But sometimes, this is what we saw in lecture 4, it's important to understand the hardware down, because your model can significantly change and exploit better the hardware. So this is one of my goals for these 5 weeks, is that look to the hardware, even if you are a software person. And if you are a hardware person, say look to the application. Because this actually, I was very happy to see this keynote. It was also a bit the summary of the keynotes. And actually is also the reason why the people in this summer school, they're putting us together. So I'm really the vertical person here. And again, it's more giving a methodology rather than give a solution for everything. Because this I'm telling you already today. I'm unable to give you a solution for everything because everything is linked to the application you have in mind. These things here that you saw before is the best you can do with the electronics. And then there are options, many of them. And of course, there is boundary, there is difference between them, as you mentioned. So there, as you asked, there is more going in programmability, more microcontroller are not the best. Actually, the reason why they burn the microcontroller is for cost. They are there because they are costing nothing. No one was thinking to do on top of it machine learning. Now the trend is changing. Someone is doing the machine learning. Fortunately, the CNN are doing Mac operation. Mac more or less is able to do. You can do an ARM Cortex-M4. My ARM Cortex-M4 burned before anybody was using, not before neural network was there, but anybody was using neural network for ARM Cortex-M4. Is able to do it? Yes. Is the best to do it? Depends on application. Because if you're constrained in spending 0.5 cents, you might have some constraint. Of course, there is no magic. No magic in electronics, no magic in compilation, no magic in machine learning, no magic in software, no magic in hardware. Whatever you're doing, you know very well this. In your field, there is no magic. If someone is doing something better than you, because they found a way to take the trade-off of everything. And in silicon, even worse. There is no absolutely magic. There is transistor with very, very clear physical rules. I'm electrical engineering. I even don't know very well the physics, but are physical rules. I studied 25 years ago, are still the same. Nothing changed. Nothing. So no one can create, Tesla, Google, whatever, can create a magic transistor. They just can aggregate the transistor in different way to make a function more efficient. Also, they have in mind the application. Actually, the table that we were yesterday were very nice talks. So actually, was the guy did the keynotes with me and was saying exactly this. So Google, and I agree with him 100%. Google, Tesla, they have now in mind a single application. They remove whatever is done as doing hardware. They are doing hardware. The people, they will employ any other person in US that is available because they are trying to do their own process. Because they are very clear in mind what they want to do. And application specification and requirement. And they might design a different. With the magic, no. They have exactly the same design tools that you have. And that they have more or less the same technology. Someone can go more sub-threshold, someone go in other, but more or less the things are there. And I think this slide, I'm talking too much and I'm repeating the question, but in general, what I want to show is that actually inside even a single IoT network, there are many, many different processors. So there is microcontroller, processors, GPU, and what is the best? They did bad. This slide comes from a Texas instrument, so you can see the old Texas instrument. In reality, also the same company is doing many of different system-on-chip processors for covering different applications, different requirements, different specifications. They are not clever. They are clever. They are doing because according to what they are putting in this processor can be a different. This is because no one can tell you this is the best for this node if it doesn't give you exactly the specification that is in mind. And what we are going to see a bit more in this course is microcontroller for many reasons. One, that today are not only for cost, but also are the one that are achieving more lower power, even if there is high power. But you find a lot of microcontroller in the range of what I mentioned before. We set a boundary of around 50 milliwatts. When I'm doing the energy harvesting, you also will see better why I fix this boundary for these 5 classes. And because they are very popular, these are more marketing, just to show that what probably many of you, I saw also in the talk, in the other talk, are interested on microcontroller. Of course, also to high power computing. You have a question? Yeah.
Again, out of curiosity, and as a soon-to-be a low-power designer, given that a thing like in
Yeah.
the terminology,
Yeah.
is a node, right? Thing and node here in this course.
Yeah,
are
it's the
ident-
same, yeah.
Okay. So a thing can take in information through sensors and it has a processing element in which it does the computation. And then it can communicate with other sensors through some modules like communication
Yes,
devices.
so it's ending somewhere else.
Yeah. Okay. So between these three, I wonder which part consumed the most amount of power.
This is interesting because traditionally is the wireless communication, even if now this is a bit changing. And actually, for making space of tiny machine learning, I removed the wireless communication from my overview. We'll talk very, very little. But I will say that actually processing information is well known to do it. As is application specific, also the communication, because now you might have. I put it in a way that if you have anyway latency constraint, there is no wireless communication that will save you. This is because I put a boundary, so I need to put boundary to be convincing. Otherwise, you have 50, you have many. No, for me it's better. No. These are boundary. So let's assume that we want to go in something very, very. You need latency. If I transmit this information, these things was going much slower. And again, it's pushing the max. Of course, then if you are using a bigger one and with a much faster motors, you might go faster than it. But again, we are not at the max here because I reduce it. But in general, we can put the boundary of the latency. But in general, again, I'm not one, I won't convince you to go in one or the other. It's the application. In general, there is a good spread now on the communication, processing, and sensing. And it all are going down with the power consumption. Processing start to be very similar to the sending, but if you add the latency, you are, we can say that should be the more energy efficiency. But to reply at 100%, I should take the application in count. And as for the all, I don't want to again make too out of time for the lunch. And as I mentioned, the last will be probably the most interesting part of, or at least the key they want to leave. So I left also up some very important information. We need to see the full system, processing can be done close to the sensors, and we now focus in one category. And again, I work also with FPGA, I work with the GPU, so I don't want to sell you anything. So it depends on application what is the best. But let's focus in one category, but this is valid for everything. Also for microcontroller, but this, if you work with GPU, is the same. Clock speed, what we want more? Faster, with more operation per second, speed, more latency, so to increase to reduce the latency, memory, etc., etc. But as I mentioned, there is no magic. And then I close here, I will go to the conclusion. Why there is no magic? Why I say even if I'm electrical engineer, and probably most of you, they need to study this formula. The magic the no magic come from where the powers go in CMOS technology. So let's focus now on design CMOS. This was also what the keynote explained. But in general, there is trade-offs. So why I'm sure that there is no magic? Because this formula, even if you are Tesla with 1 million of people working, you need to respect this formula. Because there is no magic if you are still in CMOS. When you move to another technology, we can talk about it. And there is a dynamic power that is depending from the frequency, the voltages. More you go down, more you're saving power. More you're down with voltage, what is happening to your frequency? You have a slower transistor. So there is trade-offs. So let's go in another. There is then the other power. Same here. Frequencies, velocity is going to increase your power. So why the curve of the keynote yesterday was showing that more you need a dissipator, more you had more computational power, because we were increasing the frequencies mainly, and we were increasing the size to put more transistor in area. Power increase. Then in general there is also the power due to leakage. You can reduce the voltage. You trade off with the frequency. There is more techniques that are progressing, fortunately, to attenuate it. But still, we are 100% linked to this formula that has trade-offs. Again, this you can read in the in the slide, but I feel the majority of people are aware of, even if you are not from electronics or you are not from chip design, you are aware around 100% that more you increase the frequencies, more you have power consumption, more you use the activity, means more you have more transistor, and more you are consuming, and there are these three elements. And these are really what are linked to the transistor. The more transistor per area you have, more you have other effect, the leakage power and the short circuit power consumption. So what I wanted to say here, so I think again, these three slides you can also go directly. That it's a work of trade-off. Don't believe, unless you don't come with a formula, but there is no magic in any way. Also, if you are doing an architecture, as you say that you are a low power design, I'm pretty sure you are doing power performance trade-offs. Even if I don't know you, but just you say low power, I'm tending to be low power, and the trade-offs are more or less there. We cannot move this because I will never believe in magic. Then for some application you can go more and an harder accelerator and more area because you need really to push on energy. Sorry, on latency, on computational resources. But you pay it in a size of your chip much bigger that is consuming power, static power. So you try to switch off and on. So inside to the system on chip, there is no magic because there is all linked to this very nice formula done from some physicists probably that link us a force electrical engineering to be creative without jumping the magic with trade-offs. So without knowing him, and he's, I don't know what he did, but I'm pretty sure he will tell my processor is the best energy efficient for this convolutional network, for the new trend of temporal convolutional network, transformer. Because if you don't put trade-offs, you cannot say anything. You can even not start to do a clever job. And this is the same on a system. So wherever you are, remember, your clever job in a system, sorry, in the chip design, on the software, has to be done or can be done there. And again, while we are stressing low power, and then I think I have only 1 minute, so I need 2 slides to show you, is again, back to really extreme, having some things that can be longer, having permanent batteries. So this is more or less what I'm putting in the topic, but this will be true, and we will see already from tomorrow, from the fact that in general, what we want to do with this clever power management is trying to optimize the use in active mode, or when you are processing the information from mode, to make an energy efficient system. But this we are going to see for next week. Sorry, I'm used with the normal teaching, there's 1 per week. So we are seeing tomorrow. And also we are going a bit to see that actually these clever trade-off are going also on the fact that we can link this formula with a real implementation of microcontroller. Again, if you come from the hardware design, you are going trade-offs. So either you switch off area and clock to go in shutdown mode, or you go in here in dynamic mode using the right voltage according to the megahertz of the speed that you want, but there is no magic. This slide I'm putting here just to say there is no magic on it. There is trade-off, optimization, and selecting the best microcontroller for your application. And again, microcontroller and general architecture of microcontroller, we are going to see tomorrow. So now I'm perfect in time. Maybe this also you can read the conclusion, take away what you're going to see, but I think we stress a lot. But before, maybe the last 2 questions, if you have any, and then we are in time for the lunch. Questions? Or you are want to run before the others to the lunch? Curiosity? Anyway, I'm here around more or less all the afternoon. Yeah?
Yeah, I didn't understand if in the drone you have the GAP9 or the STM.
This is my surprise for the end. So at the moment, this demo is 100% in ARM Cortex-M4.
Okay.
So this also to say how this comes from the benefit of using these sensors that are already doing the processing on it. So we can offload the processing power thanks to these sensors, because they need just the signal processing, the machine learning is much simpler. Because tomorrow I'm showing the sensor and the processor.
But will they be compatible with the GAP9?
No, sure. With GAP9 we have computational power that we are doing sensor fusion with camera. Exactly. So this was for the demo. This was even to show that even an ARM Cortex-M4 that has nothing is able to run an autonomous system. If you want to add complexity application function, there is a full free room to do it. Yeah, thank you. Okay, yes. Yeah, sure.
I was wondering, I'm working on optimizing deep neural networks to deploy them on embedded systems.
Yeah.
So usually my target is to have a model that execute faster, can fit in small devices. But I was wondering if I want to add the aspect of the energy consumption, how much does it affect the operation we do? Like if I'm working with binarized neural network, for example, I can remove matrix multiplication and use bitwise operations. Does it affect also the energy being used?
A lot.
A lot, okay.
Because basically, this is because I'm saying energy and latins are going 100% together. This as I went fast because tomorrow I'm starting from here. But what happened is that if you remove complexity, let's say operation, what you do in changing from a matrix multiplication to another, you remove complexity. You just the energy, the peak power is the same because your processor is active at full speed to do it. It's changing little, but if you save half of the time with your hardware software optimization, you have half energy, half latency. This is because again, I see the things, the really two phases of the same issue, making the job with the minimal execution time and help energy, and is helping also the latency. Then there is much more because the system is bigger, but in this case it's exactly the same. Okay, good. Okay, so thank you very much. Enjoy your lunch, and again, I'm here for question, cooperation. Also, actually, I have a very active group on this topic. So if you are interested, thank you.